available. It wasn't the most correct answer, but it was the best answer available. So yeah, exam 2 is not going to get regraded. All right, first example is balancing an acid or base, or balancing a redox reaction in acid or base. We're going to go all the way to base because
Base. Oh, dang, that's a lot.
that's the one that's longer. So let's do this one together. This is quite a process. Takes a bit of time.
It's because we have to go through acidic conditions to get to basic, right?
Right.
Okay.
You're going to need your oxidation rules available to you to do these questions. So make sure you have your oxidation rules on your note sheet. All right, I'm going to blow through this, and if you have a question, throw it in the chat or unmute yourself. Yes. I got you. Hold on.
Is that S3? AS2S3?
AS2S3. Thank you. Yes.
Okay, thank you.
Hold on, Ian. I'm making it happen. Okay. You should be good now.
Recording in progress.
Okay, let's do this practice problem. So step 1, well, let me do this. All right, step 1 is determine species oxidized and reduced. If you're my student, you've heard me do this a million times. I'll give you some advice about this kind of problem. If you find that things are not working out as you're going along, like numbers get weird or they don't match on the left and the right, just start over. All right, so we're going to do species, or first you got to figure out the oxidation state of everybody. Let's see, nitrogen is +5, oxygen's -2, sulfur's -2, and I think this is arsenic. Don't know. That's +3. You have to know how to figure that out. Hydrogen's +1, oxygen's -2, AS is now +5, sulfur's 0 now. Now nitrogen over here is +2 and oxygen's -2. That's got to be quick for you because, of course, it is a timed exam. Okay, so next step is write your half reactions. Write half reactions. This is called the half reaction method. If you want to look this up and watch a few examples being done. So we want our species oxidized, the guy that became more positive, where electrons are going to be a product. Electrons are going to be a product. So the guy that became more positive, went up, is AS. He went from 3 to 5. So you bring down everybody that he's attached to or everybody that he used to be. Sometimes things will break up into more than one thing. You can see that sulfur is in its elemental form on the other side as the product. So we need that as well. So we're going to include sulfur because sulfur used to be attached to AS. So everything comes over. Okay, now we do species reduced. In your reduction, electrons are a reactant because you take them onto you, you become more negative. So the guy who went down, reduction sounds like down and oxidation sounds like up. All right, the guy that became more negative.
Does oxidation sound like up?
Yeah, it does. It sounds like up, like happy, like oxidized. Like I want to be oxidized, you know? It's like a positive notation. All right, so we've got nitrogen has gone from +5 to +2. He's gone down. All atoms are male, by the way. Never met a female atom in my life. Okay, so now next step is now we're actually going to begin to balance. And you balance things in a specific order so as not to make your brain explode. We balance all atoms other than hydrogen and oxygen. Those guys get their own process. So I need to take care of my sulfur. And sulfur needs to have 3. And my AS needs to have 2. So I have balanced my AS and my sulfur. And then on the bottom, my nitrogen is chilling, so I'm good. Now we go to, yeah, that's a good acronym. And also Leo says GER is another acronym. Leo says GER. Loss of electrons is oxidation. Gain of electrons is reduction. Oil rig is also another acronym. Oxidation is loss of electrons. Reduction is gain of electrons. All right, next step is to balance our oxygen first. So we balance oxygen, and this feels weird, but we're going to add in a whole water molecule. Everywhere we need an oxygen, we add in a whole water molecule. All right, so on my oxidation reaction, I have 8 oxygen on the right, so I need 8 waters on the left. I've got 2 times 4, that's 8 oxygen. And then on the bottom, I need 2 waters on the right because I have 3 oxygen on the right. Next, we're going to balance hydrogen. We just messed up hydrogen because we added a bunch of hydrogen with our waters. So we're going to balance hydrogen with H+. So everywhere we need a hydrogen, we're just going to add a whole H+. Don't forget the plus. That's going to be important whenever we go to figure out how many electrons this reaction is transferring. Okay, so on the left of my oxidized, I've got 16 hydrogens. And on the right, I've got 6 hydrogens. So I need 10 H pluses on the right to bring my hydrogens to 16. And then on the bottom reaction, I have added in 2 waters, which caused 4 hydrogen to come into the game. So I need 4 hydrogen on the left. Now we're going to start to balance our electrons. This is the point at which you might determine how many electrons were transferred in the reaction. If Mark asks you that, this is how you figure it out. So you balance charge with electrons. Each electron brings in 1 charge, or plus -1, brings in a -1 charge. Okay, this is how I do it. I draw a line in the middle. I look at the total charge of all the atoms. I add them all up. This guy's neutral, water's neutral, AS sulfur's neutral, so it's 0 on the right. And then, or on the left rather, it's 0, and on the right, it's +10. So I need 10 electrons to get my 10 to go to 0, and now they're matching. I've balanced my charges. Then on the bottom, I do it all over again. On the left, I've got a +3. Figure out why I'm saying that's +3. And on the right, I've got a 0. So I need 3 electrons. Next step, that'll take me down to 0. Next step, balance electrons. So we just added in a bunch of electrons, And now we need to balance electrons. This is not 10 OH, this is 10 H plus. And that's because we have 16 hydrogen on the left and only 6 hydrogen on the right. And so I needed 10 more hydrogen to balance my atoms. All right, now we're gonna balance electrons across both reactions. And to do this, you multiply them by some factor that makes your electrons equal each other. So this can make things get kind of weird. So the top reaction, I need to multiply by 3. And the bottom reaction, I need to multiply by 10. Because I need my electrons to be the same. I put 10 electrons on the right because the left side equals 0 and the right side was plus 10. And so I need the left and the right to have the same charge. So I added these 10 electrons to get that plus 10 to go to 0. Okay, so times 10 down here. Now my new reaction is 30 electrons plus 40 hydrogen plus 10 nitrates makes 10 NO gases and 20 waters. My new reaction here is now going to be 24 waters plus 3 arsenic sulfides, I think that's called, I don't know. And then 6 arsenic acid and 9 sulfurs and 30 H pluses and 30 electrons. Old reactions don't exist anymore. New reactions are all I care about. I add them together. So that's our next step. The plus 10 is coming from these 10 hydrogen right here.
There's 20 waters in the
Bottom?
total. Yeah.
Thank you. The plus 10 is coming from these 10 hydrogen right here. 10 plus 1s. So that's plus 10.
Protons.
Indeed. Number 8, so we balance electrons, and now we eliminate spectator ions. So anything that matches the left and the right of your reaction, anything that's the same on the left and the right. No. Sometimes you can have waters and OHs on the same side. But there are no OHs on the screen right now. We have not added any hydroxides. You're looking at 40 H pluses right here. This is 40 H pluses. Okay, so we eliminate spectator ions. What can we get rid of? You always need to get rid of your electrons. If you can't get rid of your electrons, you didn't do it right. Always need to get rid of your electrons. And we have 40 hydrogen on this side and 30 on this side. So I can get rid of 30 hydrogen. And that will leave me with 10 hydrogen. And my waters, I can get rid of waters. So I've got 20 waters on the right and 20 on the left. So I can get rid of 20, and that'll just leave me with 4 waters. And that's it. You're done with acidic. That's the acidic answer. So if the exam has acidic, this is where you would stop. So we've got 4 waters and 10 hydrogen. That's why it's acidic, because it has excess of these guys. This is what makes it acidic. And then we've got 3 arsenic sulfides. And on the other side, 10 nitrates. Then I've got 6 arsenic acids. I guess that's it. I don't see anything else. Okay, that's everybody. So this is balanced in acidic media. The number of electron transferred is 30. Okay, now I'm going to go to basic. Step 9, add an OH for every H plus that you have. So we need 10 OHs because we have 10 hydrogens, and you have to add them to both sides of the equation. Uh, 30 electrons were transferred right here. 30 electrons transferred. And here, 30 electrons transferred. So that came from doing step 6 and 7. That's how you get your number of electrons transferred. So they're transferred from the reduced reaction from the oxidized reaction to the reduced reaction. It's added to both sides because anytime you do something to a reaction, you need to add it to both sides of the reaction. You can't change the mass of a reaction. Okay, so we're adding OH for every H plus to both sides of the equation. And then number 10, form and eliminate excess water. So this is what this looks like. This always confused me when I was a student. I didn't get it, but that's embarrassing because it's not difficult to understand, but to me it was difficult. This makes 10 waters. So 10 hydrogen and 10 hydroxide makes 10 waters. Now you need to eliminate any excess waters, which we don't have any on the right. We just added to our water situation. So we now have 14 waters on the left because we had 4 and then we just added 10. So this is my answer, balanced in basic media. And you know that you've got it to basic because now you have an excess of OH, and that is a base. Questions?
So, you basically got the 14 by the 10 H2O you circled and the 4 H2O?
Yep. Yeah, you add those guys together. Yeah, indeed.
I had a question.
Yes?
Why did you add 10H plus in the first equation when you had 8 hydrogens on the left side and only 2 on the right side?
Let's see. Okay, in the first...
On the left,
On the left, I have 16 hydrogen. And on the right, I had 6. So on the left, I had this many, 8 times 2 is 16 hydrogen. And on the right, I had 2 times 3, which is 6 hydrogen. And that's why I needed
I see.
Okay,
Thank you.
you're welcome. What else? Think we're good here? All right. Marinate on that a minute. Let me get a couple more. Let me see where we should go from here.
The 8 oxygen on the 8 waters on the left is to balance the oxygen on the right.
All right, let's move on. We're going to talk about thermochemistry now. We're going to do a bond dissociation enthalpy problem. I don't want to do a Hess's law problem again. I feel like you guys are maybe okay with that, and we practiced that so much for the quiz. So know how to do Hess's law. You'll have a Hess's law problem, but maybe we haven't practiced bond dissociation enthalpies enough. The electrons transferred, they're not calculated so much as you arrive at the electrons transferred. You figure out how many electrons you need to balance the charges of the equation. So if you look at step 6, that's balanced charges with electrons. So I looked at the charges on the left and the right of my reaction, and then I added in how many electrons I need. So you don't really calculate them, you arrive at them by balancing your charges. And then on the top reaction, I had 10 electrons on the right, and on the bottom, I had 3 electrons on the left, and then you need those to balance each other. So I had to multiply the bottom times 10 and the top times 3. And so that gives me a total of 30 electrons. No worries. This was a difficult example right here. I would not expect you to have a problem this difficult on the exam, but you know, it's good to do the more difficult practice problems. All right.
Yeah. Also, like sometimes you'll have like a much lower common factor than just 10 and 3.
Yeah. Don't be afraid of the numbers that you see in these. Sometimes they get really weird and big. So the electrons get added in on step 6, balance charge with electrons. Yeah, so I would kind of expect him to write out full answer choices. Yeah, I would expect that. Because if that's what you're expecting, then you're ready for all things. So see how I have written here, oxidized electrons are products. So that means they go on the right. And reduced electrons are reactants. So that means they go on the left. Yeah, so that's one easy way for him to ask you about this. Like he might ask you how many waters are in the balanced are in the redox equation balanced in basic media. Or he might ask you how many electrons were transferred. Or maybe he asks you how many excess hydrogen do you have in the acidic one. But if you expect him to ask you the entire answer, the entire balanced answer, then you're good to go for all things. Then you're capable of doing all things. All right. Let's talk thermochemistry. So for thermochem, we need to do Hess's law. We need to do bond dissociation enthalpies. We need to be able to calculate how much heat a reaction will form given certain quantities. So let's do one of those guys. So thermochemistry is our focus now, and then yeah, we will get to neutralization and pH for sure. Let's knock thermochemistry out first. I think probably the neutralization concepts and the pH concepts are going to be the most difficult. I feel like you guys have had the least amount of preparation for those concepts. So spend some time on those tonight. You know, the exam's tomorrow, so it's whatever. All right, here we go. Let's blow through a bond dissociation enthalpy problem. Okay, so for these problems, or for this type of problem where you are given some table of bond energies, either you're going to be given a table or they'll be listed out, and you'll have a reaction. And the question will be, what's the enthalpy of this reaction? And so the equation that you need, enthalpy of reaction is equal to the sum of the bond energies broken. I'm going to teach it the way Mark teaches it. He does plus the sum of the bond energies made. $140. I just made these numbers up, by the way. And for the bond energies made, change the sign to negative. All of the bond energies will be positive. For the bond energies of the bonds made, change the sign to negative. Okay, so on the left, these are the bonds broken. And on the right, these are the bonds made. The bond energies will definitely be given in the problem, for sure. But something you need to watch out for, I'm not sure how he's going to give you the bond energies, like if he's going to give you more than you need. Make sure you're looking at the correct number of bonds. For instance, a C single bond O is going to have a different bond energy than a double bond, than a triple bond. So make sure you're finding exactly the right bond. Okay, look out for that. All right, so you got to draw the Lewis structure. For the most part, I recommend drawing the Lewis structure to know, to be able to properly count up the number of bonds. So here's the first guy, propane. And then the next guy is O2. Maybe you're like, how am I supposed to know the Lewis structure? Well, because that's legit part of the course. Yeah, we have to balance it. Yep. And that's going to be kind of ugly because this is a combustion reaction. So here's our OH. And then I've got CO2. So if you suck at Lewis structure, here's what you do. Look at what he's given you. And then, like, for instance, you would know that the oxygen bond is a double bond because that's how it is in the problem. And that the carbon dioxide is a double bond because that's how it is in the problem. So the chart given might help you a little bit. But yes, we definitely need to balance it first. And this is a combustion reaction. And combustion reactions, we want to balance in the order of CHO. It's just helpful. You don't have to. It's just helpful. Start with carbon. I have 3 carbons on the left. I need 3 carbons on the right. Then move on to hydrogen. I have 8 hydrogens on the left and 2 on the right. I need 8. And now do your oxygen. I have 6, 10 on the right. I need 5 on the left. Now, if it didn't work out for you smoothly like that, then you made a mistake. Start over. Erase your coefficients. Start over with carbon. So what that means is we have to multiply our bonds by the coefficient. So we have 1 here, and here we have 5. And here with water, we have 4. And here with carbon dioxide, we have 3. All right, so listing out the bonds. Just break every bond that is existing in the reactants and make all the bonds that are existing in the products. So I've got 1, 2 carbon-carbon bonds. So carbon-carbon is 110 times 2. And then I've got 1, 2, 3, 4, 5, 6, 7, 8 carbon-hydrogen bonds. Somebody check my work, make sure I'm doing this right. Looks good to me. And then I've got 1 oxygen bond, or double bonded oxygen, but 5 times. So my OO bond is 5 times 60. Okay, all of that business are my bonds broken. Bonds broken. So let me throw that in my calculator. Which, by the way, I have somebody's calculator. They were at my office hours on Monday, and I jacked your calculator because it's exactly the same calculator as mine. It's a TI 30XS. I'll have it with me in the morning for the exams. So just come up and get it from me if I have your calculator, a TI 30XS. Also, don't forget your calculator tomorrow. So many people forget their calculators. Stop doing that. 110 times 2 plus 140 times 8 plus 5 times 60. 1640? Okay, let's go through the pane of the right. We have these kind of questions is where your terrible obsession with colored pencils and pens comes in clutch. So we've got oxygen, hydrogen twice times 4, that's 8. That's a total of 8 oxygen, hydrogen bonds. So 75 times 8. Yes, indeed. And then we've got 1, 2 carbon double bonded to oxygen times 3, so that's 6. So that's 105 times 6.
Bro, what is going on?
That's C double bonded to oxygen. All right, 75 times 8 plus
1230?
Yes, yes, yes. Okay, this is the one that we make negative. Negative. So you're literally just subtracting. So I don't want to throw you guys off. I know it's the night before the exam, but if you just change your equation to be subtraction in the first place, you don't have to worry about this changing the sign business. Okay? But the reason I teach this is because that's what's in this PowerPoint. All right, so delta H of reaction, 1640 minus 1230.
Or 10.
For 10, indeed. So I just made these numbers up, but normally combustions are exothermic. And this is endothermic because I made the numbers up and they're not correct. So a negative enthalpy is exothermic. I believe he will ask you about this. Very common thing to test on. And a positive enthalpy is endothermic. And that's it. Questions about this business? All right, let's move on to, so the other one that you need to practice is Hess's law. And then we're going to do another practice problem right now on just determining the amount of heat released from a reaction at specific quantities. Yeah, really good question. Let's talk about the potential energy and all that shit for sure. Let's go over it. So, let me continue to attach things to these words. Exothermic means many things. It means that the potential energy of the reactants is higher than the products.
Or a positive enthalpy.
Indeed. Also, the bonds of the products are stronger than the reactants. Life wants to make the stronger bonds. Life wants to exist at the lowest energy it can. So a exothermic reaction is favorable. This is the natural reaction that life will do, that the universe energetically is okay with happening, because energy is released, heat is released into the world. Your enthalpy is going to be negative. Your Q is going to be negative. That energy is being released into the world because the bonds of the product are stronger. Stronger bonds are going to release more energy than weaker bonds. And if you drew what we call a reaction progress diagram, it would look like this. This represents potential energy. This would be the reactants, and this is the product. So the products are at a lower, chiller energy than the reactants. Yeah, go ahead, hon.
It is written that the potential energy of the reactants in higher products.
Oh, potential energy of the reactants are higher. Oh my goodness. All kind of weirdness going on right here. Potential energy of the reactants are higher than the products. Yes, yes. All right, let's go the other way with it. Endothermic. Everything is just the opposite. This is the universe does not want to do endothermic reactions. It has to add energy into the system in order for these guys to happen. And it's because the opposite thing, potential energy of the reactants is lower. So the reactants are more chill than the products. And so for this to happen, we have to add energy into the system to create a higher energy species. So potential energy of reactants are lower now than the products. So in chemistry, high energy is bad. That's not what the energy of the universe wants. The energy of the universe wants to be low, in the lowest state possible, lowest state energy. And what this means for bonds is the opposite thing. The bonds of the reactants are now stronger than the bonds of the products. And if you want to make a weaker species, you need to add energy into the system. No, it's a good thing. It's a good thing. You don't want to expend energy. You want to be as chill as you possibly can. 0 point energy is always the goal. So the bonds of the reactants are weaker than the bonds of the product. As you go on in your journey in chemistry, you're going to find that the universe wants to be symmetric and at the lowest energy possible. And oddly enough, it wants to be able to exist in the most amount of ways possible. So whenever you get into, hold on, let me draw this shit without messing it up. What do I want to do here? Okay, like this. So when you get into Chem 10, you're going to learn about entropy, delta, yes, exactly, delta H or delta S. And you're going to see that the universe wants to exist in the most amount of states it possibly can. The universe doesn't like to be boxed in. We always want to be increasing disorder and achieving symmetry. It's pretty wild. It's pretty wild. Yeah, just like that. Smack them. All right, let's do another problem. Let's do the last thermochemistry problem, and then we'll move on to neutralization, acid-base, pH. And we'll do a few of those. Okay.
Oh my god.
Okay. They updated my whiteboard and now I don't know how to erase the whole whiteboard. All right, next problem. Now we're going to think of our heat term as being an actual species, a molecule, which again, if you're my student, you've heard me say this stuff so many times. I know. But let's do another example problem. I want you to think of heat as being a molecule. And hopefully this will make sense to you. Let's just do a typical combustion reaction. We don't need to get fancy or cute or quirky with whatever kind of reactions we're doing. All right, we're going to balance in the order of Cho. Carbon 1, hydrogen 2, 4. I need 2. Oxygen is at 4. I need 2. Okay, I'm balanced. Okay, here's the question. Oh, wait. I should get more clever with this. Wait, bad one. I know what I need to do now to be to make more sense. All right, we're going to do zinc and we're going to do hydrochloric acid. And we're going to make zinc chloride. That's going to be aqueous, and we're going to make hydrogen gas. Okay, here we go. How much heat is produced I also need to give the enthalpy of the reaction, negative 75 kilojoules just kilojoules. Okay, how much heat is produced when 4.20 grams of zinc are reacted with 15.5 mils of 6.05 molar HCl. All right. First of all, what the hell, right? We've got molarity, we have heat. We want to know how much heat we're going to make. It seems scary because this reaction makes this much heat. Like, why is that not the answer? So the amount of heat that is listed in this equation, which it is now called a thermochemical equation. Once you attach a heat value to your equation, it's just called a thermochemical equation. Another way you might see this is that heat might just be sitting as a molecule. So it's, the value was 75. So it would just be plus 75 kilojoule. And that's how I'm going to leave it, because that's how I want you to think of it. But I'll put this again up here. Because the heat was negative, because the enthalpy was negative, that means this is an exothermic reaction and it belongs on the product side. But if the heat was positive, plus 10, then it would belong on the reactant side because it would be an endothermic reaction. Now, it doesn't matter where you put it. You don't have to put it anywhere. I was just trying to teach you something else. Okay, so we want to know how much heat we can make. We have starting reagents, so be like me. Write your stuff underneath where it belongs. So we've got 4.20 grams of zinc, and then we've got 15.5 mil of a 6.05 molar solution. So you did this in lab this week. You had to find the moles of limiting reagent to divide by your Q value, or maybe you haven't done your lab calculations, but that's exactly what you did in lab. Indeed, thank you. Very important. We do need to balance it. So in lab, you did Q reaction over moles of limiting reagent. So that's what we need to do here, is find the moles of the limiting reagent. And yes, first let's balance. We need a 2 in front of this. Nope, my bad. We needed a 2 in front of that. And now we're good. So we want to know how much heat we can make, and just like we learned how to find the theoretical yield of a reaction, we're going to turn our two starting materials into a product, and that product is going to be heat. So we're going to start with zinc. And we have 4.20 grams of zinc. I'm going to turn it into moles so I can turn it into moles of my heat. Okay, zinc weighs 65.37. And then whatever coefficient is in front of zinc is the amount of moles related to this much heat. And there's a 1 in front of zinc. So 1 mole of zinc yields negative 75 kilojoules of heat. So this will be one possible yield of heat. Now we're going to do HCl. This is what students don't know how to do because it's molarity. But when you're trying to turn molarity into moles, you multiply it by the volume.
No, I just let the computer.
And we have 15.5 mils, but we need to turn it into liters. So that's 0.0155 liters of HCl. And that's going to be multiplied by the molarity, 6.05 moles of HCl per 1 liter. That's what you do with molarity. You need to turn it into a unit conversion factor that's useful to you, like so. So it's almost like that big M is holding your information hostage. Nobody knows what to do with the damn thing. Well, this is what you do with it. You turn it into the unit conversion factor. So the value goes with the moles, and it's always 1 liter of solution. Okay, then we're going to turn it into moles of the heat. For every 2 moles of HCl,
Oh, bro.
there's equivalent 75 kilojoules of heat given off in this reaction, and that comes from the coefficient 2. So that's one other possible yield of heat. So this is just like finding a theoretical yield. But instead of doing an actual product, we're doing heat, which is a product in this case. This is how much heat is produced.
Oh my god.
So this is my theoretical yield of heat. I can't make this extra heat. That's my excess heat. You can think of it like that. Questions?
Oh my god.
It is the heat, yeah, but we're still going to maintain the integrity of the sign. So because the enthalpy is negative, it's the heat is still going to be negative. So it is also the sign, the magnitude and the sign. No, we choose the smaller value. We choose the smaller value.
Then wouldn't the smaller value be -4 instead of -3?
Oh, I see what. Okay, it is the magnitude. It is the magnitude. Yes, it's the magnitude. I see what. Yeah, Alan, I see what you're asking. Yes, my bad, you guys. It is the magnitude. The smaller.
You're teaching engineers here.
Yeah, I know. I'm like, wow, okay, yeah. Technically, you guys are actually right. Yes, it's the magnitude. My bad.
Magnitude is just absolute value.
But the answer is still negative, though. The answer is still negative, yeah.
I'm still lost why you, like, how do you know that's the magnitude and not -4?
So this is more heat. This is 4.8187 kilojoules of heat, and this is 3.5165 kilojoules of heat. We can't make the larger amount because we don't have enough hydrochloric acid to make that much. We only have enough reagents to make this much heat. The negative sign means that the reaction has lost the heat. If it was positive, that means the reaction gained that much heat. So students are like, why isn't the -4.8 the actual smaller value? If you're saying to find the smaller value, and I'm correcting that explanation in that it is the magnitude that you're looking for. It's the amount of heat. Just ignore the sign, like Jian's saying. Just think of it as being the absolute value. Just ignore the sign.
Thank you.
Welcome. Yes, we always choose the one that makes less heat because this is a theoretical yield situation.
How would we find the excess zinc in this situation?
We wouldn't. Well, okay, if we wanted to know excess zinc, we wouldn't be turning ourselves into heat. We would be turning ourselves into a product. Like we would have turned ourselves into zinc chloride or hydrogen. In fact, let's segue into the next thing with that. How do we figure out the excess amount of something produced? So when we're talking about heat, there is no excess heat. We don't make excess heat. We just make the amount of heat that we can make.
Do you want to say anything
Okay,
to
so
repeat
when you
yourself?
say you choose the one that's smaller, why wasn't negative 4.8 smaller than negative 3?
No, there's the
That's a good question because we're just looking at the magnitude of the value, not the sign. So just ignore the sign and just think of the values, the magnitude of
Find
the
the moles,
values.
convert to one of the products. Then, in doing so, you can find the limiting reagent, because whatever you get less is the limiting reagent. I want to go to the library, bro. Fuck this.
You want to go to the library?
Yeah.
We're going anyways.
Oh, I also.
Yeah, we could turn this into a percent yield, and I was going to do that actually. Hold
I was
on.
walking around while I was on the phone with the police, and then no. I was walking around, and then I found this. Like I found a printer by itself, and then I looked in, and then I stole some paper. This never happened. Like,
Okay, we don't need to turn it into a percent yield problem, but let's do it just for the hell of it. Let's say this reaction has a 75% yield, and you want to know how much heat you're truly going to produce. You would multiply that by the theoretical yield. Same kind of process as before. So you would do 0.75 times 3.5165.
Association? Is that just talk about anything like
I was on the phone with the police.
that?
Okay. Let's move on to acid, base, pH, neutralization kind of stuff.
Who do you call?
The number I called, like, I just tried a random number from where you called because no one was answering.
Sure. Which lab?
And finally, one of them answered. And then
No, you do not need to know about solubility rules. Which lab are you talking about? The last lab? Thermo 2, number 5, okay.
we were just running that direction, and the guy's like, alright, now I know how to survive in this building. Never go to the other half at night.
It's haunted too, bro.
Yeah, it's
What's the
haunted.
point also?
Dusty.
Mommy. I'm not gonna share this video anymore.
You're not gonna share with Andrew or Alex?
They're not gonna watch it. I shared it many times.
You're right. Dude, you need to send me this shit because I literally missed an hour, or almost about an hour.
It's good. It's silence, right?
Hmm?
Like nothing's on. Like it'll be, since you missed that like hour in silence, right? Like,
Hopefully you didn't pick up everything I said. Like, dude. The woman,
that's my bad.
when I got transferred, they acted like.
So for number 5, you take your so you calculate 3 enthalpies in this lab using this equation here.
And then there's a.
So you have equation or the reaction that you did for B, which was HCl plus NaOH. You get your delta H for that.
Do this.
And then you have reaction C, which was just sodium hydroxide dissolving, and you get your delta H for that.
We did this.
And then you have your reaction D, which was sodium hydroxide dissolving in hydrochloric acid,
You're mad at that.
which is the sum of both of the first 2 reactions, and you get your delta H for that. So these 2 reactions should equal this reaction. So this is why this lab is an application of Hess's law or Hess's law.
Yeah, that's what we did. This was negative 60, negative 30,000, and then negative 90,000.
This girl in our lab is still trying to make us.
And so to answer number 5.
Or send a picture on crack courses. What the frick?
I wonder why.
It says to calculate the percent error or percent difference. And so you take your...
No, yeah, we did this basically.
So percent difference.
For every reaction.
is going to be delta H from reaction D minus delta H from reaction B plus reaction C divided by delta H from reaction D times 100. Because B and C should equal D. So it's like you're trying to find a percent error of Hess's law.
Wait, what? No fucking way. Bless you.
Thank you. Welcome to our podcast. Whoever sees this video, just let you know, you're tarantado. I'm kidding.
Tarantado.
Tarantado.
No, you don't need to know how to label a phase diagram. You don't need to know how to label a phase diagram.
It's also goggle. Gaga. Those
Let me
are
guess.
Stupid in Tagalog.
That means
Stupid.
baby.
No.
Gaga.
Gaga.
Goo goo
for-
gaga.
Oh, dang, bro. You trying to... Gago, male for stupid. Gaga, male for stupid. Tarantado,
Tonto
stupid.
tanta.
Yes, you definitely need to know Q equals MCAT for sure.
I know that. It's easy.
Q equals MCAT. And if you have a calorimeter constant, then Q equals MCAT plus
what?
CAT.
She's like, can you go down?
And this one is your calorimeter
She's like, are
constant.
you able to? And I'm like, yeah.
And this one is your specific heat.
I thought they thought I was in danger or something. But
And it's negative.
it's not the case. Not the case at all.
Pizza? Sure.
Converting to molar enthalpy means take your Q value and divide by moles of limiting reagent. And that makes it molar enthalpy. So whatever your Q value is, divide by moles of the limiting reagent. Now I'll tell you that all of the moles of the limiting reagent are 0.050 for all three reactions. That's not 100% true, but I don't have time to explain to you the details of how it's not 100% true.
I don't care about the lab.
Yo, this is over an hour, bro. Hey, buddy, look at this.
You calculate the delta H. You calculate it.
That is definitely not. Oh, wait.
So delta H of reaction
Oh.
equals negative Q of the reaction divided by moles of limiting reagent.
Did I change your life?
And this is equal to negative mass of
Your
solution
roommate had the answer key?
For last semester, right?
times
It's not gonna be the same.
specific heat of solution times temperature change. So you take that and you divide by moles of limiting reagent.
I don't know if the water is safe as
Questions, bro.
And you do that for reaction B,
quiz me.
C, and
Right now.
D.
Go do it.
Like the question.
And then you plug it into
I'll
this
write it down.
equation.
You gotta listen to the lab.
Hmm?
You gotta listen to the lab. You gotta be quiet for this. How do you do this still?
Oh, the mass of the two reactions, the reactants, times
Okay.
4.184.
Any more questions about the lab write-up before I go on into
over the
pH?
limiting reagent, moles of limiting reagent.
说跟我 pH 啊，好平啊。That's messed up.
David, I see your
Is this
question.
Amtrak?
I gotta
That's the
pull that
baby
up.
that
I
lives in
don't
Amtrak.
have that worksheet anymore.
One day the
50% relative difference is not very good,
I was about to say something.
but I had a lot of students get those numbers. My best percent difference was 0.4. I had a group get
That's Andrew?
0.4.
Chancho?
Who's this?
Pretty average seems to be about
That's
20%. That's like you did okay.
That was a direct message.
If you did under 10%, then you did a very good job. If you did
Yeah, I have to.
50%, you didn't do a good job.
I don't have to, but like, I'll go.
You study, huh?
It'd be
I have to
like
run
that
my study
though.
guide.
Check your calculations, check your moles.
Chancho.
Remember I
You know
said
what that
everybody's mole should be about
Saying Mexican
this.
slang,
So that's what you want to divide your Q by.
Well, it's probably cool.
And the Q should be
What about Peru?
roughly,
If I called you
very
Chancho,
roughly, about 40K for B,
Picked you.
C was about
No, I'm just saying, like,
60K
roughly
and D
maybe.
was
I
about
didn't give him a decimal,
100K.
usually.
Very
No,
roughly.
huh, Chancho. That's a cool name.
Big numbers. Yeah, 32% is all right.
What if I punch the
Like a
ground right
B
now?
minus.
I just want to run, bro.
Okay, back to the exam. We want to talk about pH and excess reagent and things like that.
I have not studied pH.
But I have to go pee, so I'll be back.
Bro, pH? The only thing I remember is from last semester. Hijo de su pucha madre, güey. Oh my god, I have not studied anything pH related at all. I'm not joking, bro. It's not a joke anymore. I'm kind of nervous now. What you smiling at? No, why are you smiling? Who are you texting?
That's just the answer this part.
Is there a girl?
No, it's my friend.
Oh.
Hey girl. Bro.
I can't see. I don't have my glasses. I haven't worn my glasses in a while. Oh, he's leaving. It's a private call. pH problem, I swear to God, bro. Oh my God, I'm gonna have a panic attack. Don't you want pizza? Go in there, introduce yourself. Hi, my name is Preston.
Can I get your number?
Dude, she can probably hear you.
Not you.
No, she can probably hear you.
Huh?
Yeah, you heard me. They heard you.
You do this one?
All right, let's move on to pH stuff.
That's how we roll. Bro, I'm asking you what to do with you.
I'm gonna pull up
Oh.
some problems here.
What are you doing? Was that what? Oh, yeah.
What did I do with that? Practice exam 2. No, that's not. David,
Don't
type
lie,
out
the
the
answer.
problem wording and
Don't
throw
lie,
it in the
bro.
chat. I can't find that I made for you guys. I don't have it
Oh, I didn't
anymore.
respond to
Give
any.
that to me.
I just showed you the message, that was it.
Okay, number 2 on the lab, we did that already. There was another question. Let me get to it. Yeah, that's chapter 9, problem 2. Yeah, so a gas phase reaction is what we just did. Or do you mean collecting a gas over water? Do you mean collecting a gas over water?
It's
Where are you going? Where are you going?
it says if he gives us the temperature of 2 gas products, can we determine how much product is being made with the percent yield?
Okay, I got it. Okay, I see what you're saying. Yeah, sure, definitely. Oh, okay, yeah. That was like the quiz. Okay. All right, let's do that after we'll do that after our pH stuff, and then that will actually be everything. So yeah, glad you asked about that one. All right, so for pH stuff, we need to know how to neutralize. Yeah, but post it. Post the first question on the worksheet. We need to know how to neutralize an acid with a base. So let's see. Let me show you the key to this business. Oh, here's a good one. Thrown into the chat. Perfect. There's a few things that I do want you to understand about the acid-base questions. Let's just do this one. I like it.
What is pH of a sol? What is the pH of a solution in water? No, what is the pH of a solution in which 175 milliliters of a 0.100 molarity sodium hydroxide solution? Oh my god, I don't know how to do this shit.
Alan, throw a question in the chat that is similar to what you're wanting to do with excess base, I think, or you said excess reagent. And I saw that somebody asked how to find the moles needed. I don't use the have need method.
No, you're right though.
But
No.
I think I can still show you how to find the most needed. Okay, so I think I can work that into this. What is the pH of a solution in which 175 mils of was added to 150 mil of a 0.250 molar HCl solution? Okay. So this one is kind of complicated. Yeah.
Does it smell?
Excess reactant is what's going on here.
Like this, bro?
Yeah.
Like this.
So first, step one is balance the chemical equation. So what's the pH of the solution? We're looking for pH
Bro, just do this.
in which 175 mils of a 0.1 molar sodium hydroxide solution was added to 150 mils of okay. So we're going to create a balanced chemical equation so that we know the molar ratio between the acid and the base.
I can put down my leg.
Whoa.
Watch this. Watch this.
Yeah, definitely.
Whoa.
I will show you both. I think I can make clear both methods. Okay, so we've got a balanced chemical equation. Our inners made sodium chloride and our outers made water.
Not her best one.
And then I balance the whole equation and it's balanced. I don't need to do anything. And then the stuff that I have, I write underneath.
Oh, I forgot.
So I've got
No one's gonna watch this, right?
175 mils
Huh?
of a 0.100 molar solution, and then I've got 150 mils of a 0.250 molar solution. Okay, there are so many different ways to do this problem. I'm just going to try to explain to you what's going on in the beaker, and hopefully you can determine your way to do this problem. I can show you 3 different ways to do this problem. One of them is my favorite, one of them is Mark's favorite, but I don't even want to show you either one of those. I want you to show, I want you to understand what's going on in the beaker. So we've got an acid and a base reacting together,
Tarantado.
and they're going to make water.
Tarantado.
And water is going to be neutral. Neutral? Neutral? That's how you spell neutral. So water is going to have a pH of about 7.
Oh, this is yours, no?
No, this is Chem 2. This is Chem 2.
What is the pH?
Water is going to have a pH of 7. But
I'm
you
gonna
need to
not
know,
do
do
good
I have
because
any remaining
of the events
H
that I've recorded today.
plus, which is going to make it acidic,
But at
or
least
do
know
I
can
have
get
any
a
remaining
acid.
OH, which is going to make it basic?
No,
So
you
we
look
need to
good.
figure out which one of these two we have remaining. So it's simple. Just turn both of them into moles
Fuck you.
and subtract the bigger one from the smaller one, and then
All
you
you
know
gotta
which
do-
one you have excess of.
Dude.
Let me show you how to do it.
Nah, I don't know. No, but you just have to write a good no sheet. Write every type of question on there and boom. And there's only like 7 types of questions. So. Oh, sorry, my mic was unmuted. Psych.
Some real tiny numbers.
That's right, John.
I don't even know what you said. Arbitration.
Bazzini. Dang, that's a cool name. Who's Italian?
Bazzini.
Bazzazzini.
Bazzinga. Sorry.
Yeah, they're going to be small. Okay, so look, you guys, this is how you turn your
Tarantado.
mole and volume into, or molarity and volume into moles. I've already shown you in this little episode of Study with Dusty, but this is how you do it. Molarity times volume equals moles. And I don't like to show this way because I want you to do stoichiometry always. I always want you to do stoichiometry. And it is stoichiometry, but it doesn't feel like it if you describe it like that. So volume needs to be in liters.
What?
So let's do HCl.
Molarity.
Oh, yeah, I get that.
Go ahead, hon.
Molarity times volume.
I lost you. Yeah.
I was just gonna say that molarity is moles per liter, and to get to moles, we need to multiply by liters. That's the stoichiometry.
When I was
That is exactly the stoichiometry. Indeed. Indeed.
I was like, bruh.
So we've got our HCl moles, and now let's get our sodium hydroxide moles, because we want to know
Yeah.
which one is there more of, because that's going to be the excess amount in the beaker. And whichever, however much they have that equals each other is just going to turn into water.
Watch out.
So sodium hydroxide is 0.175 liter times 0.100 moles over 1 liter. Yes, and they are going to be little amounts.
Do you know why molarity times volume gives you moles? Do you know the famous equation we learned?
Okay, so just think of this as moles of H plus, because it is. The hydrochloric acid is going
That's a good
to
equation, no.
100%
Remember this
turn
equation?
into H plus and Cl negative. So this is moles of a proton. And that is an acid. You can think of it as an acid.
Moles over liters? What the frick is this? Oh, I'm getting a headache now.
And now we have our moles of base.
So go library.
Okay, now we don't need to get cute and create methods for how to figure out how much excess we have. Just subtract the smaller one from the larger one. And sometimes you'll have more base, sometimes you'll have more acid. In this case, I can see that we're going to have more acid. So my larger one is the acid, and my smaller one is the base. So we are going to have an acidic beaker.
The bigger
By
one's
this
the acid,
much.
the small one's the base.
This is how many moles excess acid we have. Now somebody tell me how I can find the pH
he
with that.
wants some. Oh shit.
The negative log of H plus.
Yep,
Damn.
the negative log of
That's
H plus.
Yeah.
But first we have to divide it by the volume.
Like they did. Moles-
Yeah, you can just crisscross it. I mean, that is what's happening, right? So if you're
Oh,
crisscrossing it, you're like,
excess
okay, I
moles,
have
okay.
that. for one, but this one I have this
Oh
of.
my god.
And then for this one, I have this of.
No, I forgot.
Whose hair is this?
But then you would still have to like subtract the values, I guess. I don't know. Yes, have need works for this because we are essentially doing have need. Okay, so we have moles of H plus, but we want molarity. We want molarity. So we do have to divide by the volume first.
Hey, yo,
So
bro, that's not.
pH
Everyone's watching this.
equals
Don't
negative
listen.
log
Remember that.
of
Now you
H
can't
plus
share this to anyone.
or
Literally can't.
POH
Wait, yeah, it's actually
equals
pick up everything you
negative
said.
log
Now you can't
of
share it
OH
to anyone. Not even
negative.
Andrew.
Malverde,
And
don't
of
listen
course,
to Jason, huh?
OH. Nope, my bad. Wrong thing to say.
Malverde,
pH plus POH equals 14. Okay, so we need to divide our moles by liter so that we can get molarity of H plus.
Oh my god, bro.
For chemists, brackets mean molarity. Brackets mean molarity. So we've got 150 mils and 175 mils. We need to add those two guys together.
125.325. 0.325. Okay, okay.
And that's 325 mils, but I need to turn it into liters.
What?
Oh, I was just crisscrossing to show how
That's
you
not right.
can do have need,
325.
but I did not recommend that. I just recommend finding the moles of both of your guys and subtracting the larger from the smaller, and then you'll find your excess. But have need still works because all of it is just stoichiometry. It's just a different way to describe doing the same thing in your calculator. Oh, thank you. 325.
Thank you, Preston Monday.
325.
you're welcome.
She didn't even say that.
So we've got 0.0615
Thank you.
is the molarity of our excess H plus. So pH equals, because they're just hella strong and they go off of the pH scale. So the typical pH scale is 0 up to 14, but we can have negative pHs. Like the strongest acids have negative pHs. And the strongest bases will get up to around 15. So they're off the charts.
It's hour 30 minutes.
All right, everybody who is not comfortable putting log into your calculator, don't go in tomorrow's exam not knowing how to work your log function on your calculator. So it really is negative the log of this value. So figure out how the heck your calculator works. And we've got 1.21, that's hella acidic. Hella acidic. That'll burn you. Yep.
Makes so much sense.
We got that from doing this math right here. See the equal sign here? That's how we got that. This is the division. So 0.02 divided by 0.325. And yes, indeed, there are 3 more pH equations that you may or may not find useful, so I'll write them down.
Alan, what are you doing here?
Um,
In the library
a
right now.
pH,
Probably writing up
so
that.
stomach acid is at a pH of 3. So anything below of 5.5, I would be worried about.
So you left my stuff up here.
Anything about 5.5. So yeah, we can talk sig figs. I'll pretend there's a decimal right there on my 150. So I'm seeing 3 sig figs in my problem. I'm seeing 3 sig figs. I've got 3 in all of my values. So I want my pH to be in 3 sig figs. And if that's true, then my pH is really 1.211. Because sig figs for pH are actually the numbers after the decimal.
It's been a long year, Daddy.
But you're saying that Mark said to use 2 decimal places for
Whoa,
pH
now.
and POH? Okay, so the original value had 2
Never
decimal
heard of that
places.
TikTok sound.
Okay, the other
Hey,
equations for
Calm down.
pH
Hey,
are
calm off
Hey,
with
that
the
came off you. You was
hydronium
watching?
ion concentration or
He's talking about
proton
Mark. He
concentration
loves
or
Mark
H
Gross.
plus if you like is equal to 10 raised to the negative pH. The hydroxide ion concentration, if you need that, is equal to 10 raised to the negative POH. And then those two guys multiplied by each other
no. She's just showing us different
is the
ways of
reason
finding.
for the pH
Let's try
scale.
to find H plus times.
It's
What?
What the
14.
fuck is that?
So the amount of acid and the amount of base is equal to 10 to the 1.0 times 10 to the negative 14. All right, let's do one more of these in a different way. Hold on one sec, let me find another question.
When will you know how to use when to use the equations you just wrote down right now?
Did they leave a mess in there?
Well, like with all equations, it's just what's given in the problem. So in our case, we wanted the
You want to
pH.
ask them? Do you guys have Axis?
And so that means we're either going to use
No, I said,
this
do you guys have
one
Axis?
or this one or maybe this one because those are the only equations that solve for pH. Now we found in our case that we had an excess of H plus. So that means we need to use this top equation to find the pH. So it's just, you know, whatever is given in the problem, that's how you know what equation to use and what the problem is asking for.
Let's not.
Yes, I do know.
Let me
some
find
balance.
another question that's similar, but a little bit different of a skill.
Cable.
What's she working on now?
Another pH problem.
Let's do like a podcast.
Okay.
Conversation here's conversations with Preston and Jason. Today's guests, Preston and Jason.
Yo, what's up?
So how you feeling today about this midterm stuff? You know.
Thinking it's gonna be easy.
All right, so we're going to do a calorimetry problem, and it's
Yeah, I guess
going to
they-
be
Dusty, she's
combined
talking
with
over me. Go ahead,
this
Dusty.
kind of problem here.
That's right. Yeah, that problem.
Whoa.
So how do you feel about that problem, Dusty?
And then we'll do a gas phase problem,
That's for
and then
sure.
that will be it. We'll be good to go.
Yeah, the economic gas prices are really high right now.
No.
Remember that soda can?
I don't
back
know.
from the-
I don't know where you guys are
Yeah.
at.
Or that one
I
time we went
hope
to the
that you
office
guys
hours.
do very well.
I still haven't drank it. And then I told myself I'm gonna drink it once I finish.
The most
the final
important
exam.
thing that you can do, time for me to start giving advice while I write another problem on the board. The
Where you
most
going,
important
bro?
thing that you can do
Where am I going?
tonight,
What?
I swear to you, is be in a good emotional state.
I'm just gonna study.
You need to be in a good emotional state. That's the only way that you can absorb information and learn. If you're in a bad emotional state, you better figure your shit out. It's not time for that.
You.
It's time to learn and study. Yep, food and sleep. Food and sleep.
Bro, I haven't had a good night's sleep in about,
Dude, she sounded like Mark for a second.
what, sleep for 5 hours or 4 hours?
No, she's like, you're without. Oh, never mind. She means something like, I don't know.
All right, let's do
Opposite of Mark.
two more
He's literally
problems.
the opposite.
Two more problems.
Mark says don't sleep. You
And
know,
I am going to
he
show
says
you the
sleep
have
and eat
needs
vegetables.
Sleep, baby.
and my method. I'll show both. So here we go with this problem.
I thought,
You thought I was
what? Thought you were Filipino? I knew you were Filipino.
Sorry about that. I was trying to get the delay right. Okay, so we've got 50 mils of 1.0 molar hydrochloric acid
my roommates are sleeping.
and 50 mils of
What the fuck?
1.5 molar sodium hydroxide in a calorimeter.
What'd you say?
Send it to me.
Alright.
Are mixed.
That probably has a bunch of, you know what I'm saying?
the temp increases from 21.0 degrees Celsius to
Yo,
27.5 degrees Celsius.
That's gonna be big.
I like the way you switched.
Let me do this wrong. 50 million.
Calculate the enthalpy of the
Oh, I
reaction.
know how to do this one. That's gonna be a pH.
So we're back in thermochemistry,
this.
but I'm also going to turn this into an acid-base question. We're gonna do two different things with this question.
Watch
I
this.
don't want to spoil it.
Watch this.
Bro, just watch the little beginning.
So we're going to assume
Is this a joke?
the heat loss from the
That means it's a
calorimeter
joke.
is
I don't know.
negligible.
You see?
Heat lose.
What the fuck?
Negligible. The
I think
density.
there's an extra I in there
What?
after the G.
So it's not bullshit. Wait, what the fuck is this?
Thank you.
Oh,
The density is 1.00 gram per mil, and the specific heat is 4.184 joules over gram degrees Celsius. Okay.
Bro,
you can get the.
And then I'm gonna say also,
multiplying this with the.
what is the pH of the solution?
oh, this is a lot, dude. Just getting us prepared. I like it.
So we're combining two chapters in one.
I'm gonna do this. I don't want to do this now.
Now, see that word, see that phrase, what is the pH? You need to activate in your little brain, okay, that means I need to find the H plus
Oh, you want to do this?
concentration. Or I need to find the OH concentration, and then I can find the H plus concentration. Or I can find the
No, I
POH
don't really want to hear.
and then find the pH. That's your goal.
No, just let me do the recording.
But first, let's deal with the thermochemistry. So we're told to find enthalpy of reaction.
I call this the Egyptian.
I'm gonna do this.
Hey, look at that motivation right there. Buddy, come on now. I'm never taking this stupid class again anyways.
And that means we need
Okay,
delta
calculate the enthalpy.
H of reaction equals negative Q of reaction divided by moles of limiting reagent. So that's our goal. So this is equal to negative M cat
Heads underwater.
divided by moles of limiting reagent. So I'm going to plug my numbers in. Delta H of my reaction
Reducing. Now you just need a freaking Lucalola.
What the fuck is this thing?
is equal to negative. So the mass of my reaction is the sum of the two liquids that I threw together. So I threw 250 mils together, which is 100 mils. And the density of
This
the
is the
solution
lab.
is
I didn't wanna do this.
1.00 gram per 1 mil. So that's just 100 grams. So my solution is 100 grams. And then the specific heat of the solution is that of water, 4.184 joules over gram degrees Celsius. My temperature change is 27.5 minus 21.0. And now I need to divide by moles of limiting reagent. Now we're going to switch it over to
The equation.
the stuff, and we're going to figure out what is
Plus
my limiting reagent.
NaOH equals H2O plus
So step one, we need a balanced chemical equation.
NaCl.
HCl plus NaOH makes sodium chloride and water.
Let's go! Oh my god, it's so good.
And I need to know who is my limiting reagent. So I've got 50 mils, or yeah, 50 mils of both. One has a molarity of 1 and one has a molarity of 1.5.
Love all.
I am ultimately asked to know the pH. Look at what we have in our beaker. We have both of these things in our calorimeter. We've got the HCl and we've got the NaOH. We're putting 50 mils of each. One of them is at a higher molarity. Already you should know if the pH is above 7 or below 7. You should already be able to tell if it's basic or acidic. So we're going to figure out how many moles we have of our acid and our base and figure out which one is in excess. And we need to know who's the limiting reagent. So we're going to find excess and limiting reagent at the same time. So my method is to do stoichiometry. So you multiply the volume times the molarity.
I don't get it.
And then I think with the have need, you would convert the moles of what you have into the moles of what you need. So stay with me now if you want to figure out how to do have need. If you don't want to figure out how to do have need, then just ignore me and let me explain this. Let's say we had 2 moles of HCl versus 3 moles of sodium hydroxide. Let's just say that was our balanced chemical equation. So to do the have need method, you would need to turn your moles of HCl. So you would get this answer. Let's get that answer. Let's just do that part.
Dude.
Yes, that is correct. That is where the mass is coming from. And you can see the work for that written right here. Okay, let's get this answer here. This is the moles that we have. That's what we'll think of this as being, the moles that we have. Why am I putting that in my calculator? 0.0500 moles of H plus, because this is my H.
Could you give me all of you? Will you give me all?
And this is the moles of OH. Okay, and then to figure out the moles that you need, you turn the moles that you have into the moles that you need. So you need the mole ratio between the two. There are 2 moles of H plus for every 3 moles of OH. That's what we did here because I just made some fake coefficients over here to try to teach the have need method. And then you do the same thing with the OH. It's 3 moles of OH is equivalent to 2 moles of H plus. And then you put those 2 guys in your calculator and then you'll get the moles that you need. And then if you have excess moles, if you have more than you need, then you know what your excess is. But oh my Lord, is that confusing. It just takes so much more time. Don't do that, don't do that, don't do that. Just do this, just turn them both into moles, subtract the bigger one from the smaller one. And then you'll know what your excess is.
Give me all.
So we've got this many moles of H plus.
Sorry.
And we've got this many moles of OH.
Bro, what is this?
We're just going to subtract the bigger one from the smaller one.
Oh, see?
And then you have to remember who, who was the bigger one and who was the smaller one. And then you know how many moles of excess you have left over. So this is your excess OH. And now we can figure out the pH by, first we have to divide by the total mass of the solution, or the total volume of the solution, which is 100 mils. So that's 0.1
No, it's called
O.
bless. It's called bless. Say bless.
Bless up.
No.
Bless.
Dude, can you do Philippine accent?
1, 2, 3. Yeah,
Can I?
liter.
Bless.
Bless.
No, say bless.
Bless.
I just added coefficients just to make a point, just to show an example of how to do have mean. They were not relevant for this problem. I just wanted to show an example where they weren't in a 1-to-1 ratio. So 0.0250 divided by 0.1. All right, so my molarity of OH, my OH molarity is 0.25.
Heads underwater.
And I need to find my pH. So here's what you do. You can't find your pH directly from OH. You have to do 2 steps to get there. You can only find the POH. So POH equals negative log of your OH concentration.
Imperfections, even when I'm losing, winning.
So 0.602 is my pH, and then to find my POH, the measure of basicity, and then to find my pH, it's 14 minus that.
Equals that.
So we've got 13.3979. So 13.40 is my pH, which is hella basic. Which makes sense because I have an excess of hydroxide. Okay. We got to go back to the thermochemistry. We needed moles of limiting reagent. The limiting reagent is the one that you have in lesser amount. So you found moles of limiting reagent up here.
Oh.
No. Because molarity is moles over liter, and we were working in moles over here. And so we still needed to divide by the liter of the solution. And that was 50 mils plus 50 mils makes liter of solution. Okay, because we found the limiting reagent, we now know what to divide down here. The bottom is 0.0500 moles. And now I can find my enthalpy. I already found my pH. I'm big chillin'.
If you don't get an A tomorrow, you will be.
That is a big ass enthalpy. Let's turn it into kilojoules.
Wait.
53.555.
53.555. What?
Kilojoule per mole.
Oh.
And it's negative.
Wait.
So I divided by 1,000 to get it to go into kilojoule.
What the fuck?
Okay, we're gonna do a gas phase problem and then we're gonna be done. Any questions about any of this stuff?
Wait, that doesn't make sense. She got 53555 joules. Wait, hello there. 4.184 times 27.5 minus 21. 0.05. What? I got.
No, he's not going to give you this problem, but he will give you 2 problems that, so this problem is broken into 2 problems, right? So he'll ask you to find the pH of some neutralization reaction. So that's what we just did. And then he'll ask you to find the enthalpy of a reaction of, you know, so we've done 2 things in one situation. Yeah.
$5,582.
So I divided by the moles of the limiting reagent to go from heat of the reaction into enthalpy, molar enthalpy. So this is called molar enthalpy. And when somebody wants molar enthalpy, you've got to divide by moles of limiting reagent. So we found the moles of limiting reagent by turning our two reagents into moles. And because the whole reaction is in a 1-to-1 ratio, the smaller value of moles was our limiting reagent.
Bro, this is too much, bro.
I
This
divided
is
by
not
1,000
gonna-
to turn it into kilojoules because originally it's in joules because of the unit of your specific heat. So the degrees Celsius goes away, the grams goes away, and we would have been in joules per mole, but that number was big and I don't like big numbers, so I turned it into kilojoules.
Can you get sturdy, bro?
Huh?
Sturdy?
Sturdy?
Yep,
I'm not gonna dance right now.
yep. Exactly. Yes. I would expect you to need to know the Q equals MCAT equation for the exam. Yes. And also delta H is Q reaction divided by moles of limiting reagent. All right, let's do a gas phase problem. It is a theoretical yield problem, but it's going to be with gases.
Dude, is she still going? I'm going to the library now.
And then everybody needs to take a break.
And then you.
Your brain can only do so much. You might try to tell your brain to do more than it can do, but it's not going to do it. It's just not.
Wait,
You've got to prioritize, especially when night before the exam, you need to prioritize.
Who's that?
Don't teach yourself something the night before the exam. If you are super clueless on a topic, you need to focus hardcore on the other topics that you're not clueless on.
Last semester, that was the last thing we learned.
Take it from somebody who knows how to take exams.
I got it wrong on the question.
All right, here we go. Last question of the night. Remember, it's just a test. You are probably worth more than the test. Probably. All right, here we go. Gas phase reaction.
Don't look at my messages. Don't want you hearing the wrong thing, you know?
Let's do. I'm gonna do this one. I've been doing this in class a lot, but it's whatever. I feel like I have a bunch of dad jokes and I keep telling my kids the same dad jokes over again and they're like, okay, that's enough for the fucking dad jokes. All right, here is a gas phase reaction. Let me think of words to write.
You're crazy. What?
All right, so a reaction was carried out.
You can enter that conference room, you know that, right? You can enter that room and you can turn on the lights and shit. Oh, we could have hooked it up in there. It really goes to show that you can understand nothing about the processes and how things exactly work, but still get a good grade. Because I'm living proof of that. I literally don't. I don't know. No. You can go the long way. Alright. What in a while. I haven't eaten anything. I'm gonna lose weight, sure.
All right, so reaction was carried out at 25 degrees Celsius at a pressure of this for hydrogen and this for oxygen. If the reaction, oh, I know what else I needed to say. In a 7.5 liter vessel, if the reaction has a 69.0% yield, how many grams of water are produced?
Nice.
Yes. Okay, so stop squeaking. That's driving me crazy. Okay, so this is a theoretical yield problem. You have to use PV equals nRT to find moles of gas. PV equals nRT to find moles of gas. So we're still going to turn our reactant into product to figure out our theoretical yield of water based on our starting reagents, but we're not going to go gram to gram like we're used to, or even molarity to gram. We're going to go gas law to gram. So let's do H2. We want to solve for moles, and we have pressure, and we have volume, and we have temperature. So moles is equal to PV over RT. And our pressure for H2 is 765 millimeters of mercury. We have to turn that into ATM because the units of PV and RT are ATM and Kelvin and liter. So 765 millimeters of mercury divided by 760, that's equal to 1 ATM.
Oh, I'm so bad.
ATM values are always small. They're slightly over 1 or slightly under 1.
Volume gives you.
So that's 1.00658. The volume is 7.5 liters. R is 0.08206.
Oh my god.
ATM time liter over mole time K. I think Mark's R is 0.0821.
Do this.
And then we multiply it by the temperature, which was given to us in Celsius. So 25.5 plus 273.15.
Hey, police officer. How you doing?
298.65.
Oh my god, it's just P over T, no? Nah, I'm just bullshitting.
Oh.
And then we do the same thing for O2.
That is
I
0.3079.
hate this game, bro.
What's after 9?
0.7895. So it would be 90.
What's the temp?
Thank you.
Where's the
Do I have it written right?
It's right there, 25.5.
Oh, well, it would be 896 because it's 8955. Sorry.
Thank you.
You have to get a better
All right,
calculator.
and now we're going to turn our torr into ATM, and luckily for us, it is still 760 torr is equivalent to 1 ATM.
Whoever is the lowest is the new reagent.
821 times 298.65.
So that's 0.8552. I just write down numbers until I get tired of it, basically. Really, they different values. But I want to have the most correct answer always.
Beep, beep, beep.
What do we got here?
Alright, I'm saying this to somebody.
Do you want to go to jail?
If you don't mind. I have to send
What do you want to do?
0.261611.
Fuck no. Yeah, it's up to you,
Hey.
bro.
Or if you want to go
He
further,
doesn't know who I am.
101 instead of 106
Buddy,
instead
buddy,
of
buddy,
1.
hey, don't listen to Malverde. Malverde, you're awesome, bro. I'm playing.
I think that's a good level of obnoxious right there.
Yeah.
Malverde,
All
when's
right,
your
so we
birthday?
have arrived at moles of our guys, but we want to know how much product we can make. So we're going to do what we know how to do, which is use stoichiometry to turn it into moles of the product. Oh shit, I didn't balance the chemical equation. I need 2 waters and 2 hydrogens. So 2 moles of H2 is equivalent to
That's fine.
2 moles of water. The question is asking me for grams. So I have
It doesn't
one more
change
step
anything.
here.
Still the same. Oh my god, yes it does. You'd multiply this by 2. So this is more.
So
this
18.02 gram per 1 mole of water.
That's
That is the
reagent.
molar mass of water.
That's the limiting reagent. My brain is just working too
And then
fast.
oxygen, 1 mole of oxygen is equivalent
H2
to
is a
2
limiting
moles
reagent,
of
baby.
water.
Bro, does this become 2? Does the O become 2 or no? Just the H, right?
What are you talking about? That's 2 oxygens now.
Oh, my
It's
bad,
4
my
hydrogens.
Alright.
Of course it becomes 2 oxygen. Because there's 2. So that's the limiting reagent now. Yep, that's the limiting reagent. So guess what? Convert H2 to H2O. What's the molar mass of H2O?
18.
Yeah, 18. So 0. What? She did it already. Man. Divided by 18. No, times 18.02. What the fuck?
All right, so I've got a smaller value and a larger value. I'm being asked how much product that I can make. I cannot make the larger value. I don't have enough hydrogen to make it. So I can only make my smaller value.
Wait, what is she talking about? How can you?
And that is a weird
Dusty.
value.
That's
Yeah. What is it?
You probably divided by 18.
Ooh.
Instead
You
of
really
multiplied by
think you would
5.
get that as an answer? 9.42 and then the
0.6.
other 0.0.
Bro, fight her, dude.
Who knows what I did? Now I gotta. Yep. Thank you. Thank you.
Change it right now.
5.548.
I'm just playing.
All right. So this is our theoretical.
Watch this.
To get my actual, I multiply it by my percent. So times 0.69. And my actual yield of water that I can make from this gas phase reaction is 3.83
Come here, that's how you do it. Sit down.
grams. I was looking for sig figs and it looks like it should be 3 sig figs based on the question. All right, guys, I'll hang out if you have any last minute questions. Not, I'll see you guys in the morning. Good luck tomorrow. Remember, sleep, food, and good emotional state are key.
Ask her something about the study guide. You can be anything.
With the full decimal for the moles of the original, it comes out to 3.87 grams.
Very important.
And 5.604 instead of 5.548 if you use the whole big long decimal.
That's different.
Yeah, it was a chunk, which is why I was like, hey, 5.6.
That's way different.
Also, a quick question. Why do you use 0.8206 instead of 0.821?
So the more values, the more accurate. The more values, the more accurate. Just like if you're going to add 273 to your degree Celsius, we can debate about whether or not we should use the 0.15. That's pretty much what's going on, just to be more accurate. Or if you're using the speed of light, 2.998 times 10 to the 8 is far superior to 3.0 times 10 to the 8. That's all it is. You can use Mark's number because Mark will have used his number on the exam, but if you use my number, you will also arrive at Mark's answer as well.
Okay, thank you.
Welcome.
Oh yeah, also I did use Mark's number. Sorry.
Yeah, that's fine. I mean, you'll still...
So it is marginally larger than yours would have calculated.
Yo, why did he talk?
Makes sense why it was a little bit different, yeah.
I want to get
Yeah, just like a little, like, that's why accuracy matters. That's why, like whenever,
I'm kidding, Gian. You're
when we were about to go into PH, I wanted to pipe up and be like, man, this is when I just feel sad because I used to know this in like sophomore year of high school.
Yeah, you forget it though if you don't use it.
Yeah.
Use it, just like language, yeah.
But like that's why accuracy, like you want to preserve as many decimal places, as much accuracy as you possibly can, until you have to put in your sig fig things.
Always round at the end, especially in States, yeah. So when you go into Chem 10, those tiny little roundings are for the scale exactly, yeah.
Yeah.
So I multiplied by 0.69 because that was the percent yield. We found our theoretical and we needed actual. Yeah, this is about everything you need to know. We didn't go over a Hess's law problem, but you should be good to go with this.
My wallet, my charger.
Well, R is technically 0.0821, just like it's 0.08206.
It's 0.0821. Valdemar, you're forgetting a 0 there before your 8. All right, then. Peace out, guys. Have a good night.
I have a question for the chapter 9 on the lecture slide number 11. So that says the C metal like seems approximately equal to 25. What are they trying to say? Or what is that?
Okay, let me get there. Chapter 9. Or
chapter 9, 11.
Okay, got it. Chapter 9.
Okay.
Oh, my bad. I'm in the lab.
Oh, this lab.
Yeah. Get there. Chapter 9, slide 11.
The molar mass and heat capacities. Oh, this one.
Oh, okay. So yeah, this is what you needed to turn in your lab from last week. So this is specific heat times molar mass equals a constant, and this constant is actually 25.
Oh, so that thing is always go to true, right? The specific heat. Oh, okay.
Yep, the specific heat times the molar mass is always 25. This is the Dulong-Petit law. Yeah.
Oh, okay. Yeah, I remember that because I kind of like say some different version.
Yeah, I noticed that everybody in my lab sections was using a totally different version. I think they had a value of 6.5.
Yeah.
They were looking it up, and I believe the 6.5 value has different units, and that's what's going on.
I think they're probably like calorie or something.
Yeah, it could be kilocal instead of joules. Yep, that's probably exactly what it is. Let's go with this one on your note sheet.
Okay. So if you want more, okay. I was wondering because for the heat capacity, sometimes it's joule per gram. If that's the case, that means we're supposed to like convert it. For example, for the H2O, it's going to be 4.184 joule per gram, right?
Yep, joule per gram degrees Celsius. Good question. So
if you change it to like joule per mole, we have to do some conversion, right? So which means like 41.84 something like that.
Yep. So this is the specific heat capacity. If you were asked for molar heat capacity, you want to have the mole down there.
Oh, okay. So one is specific heat, one is mole heat. Okay.
Yep, and then there's also just heat capacity, and in that case, it's just joule over degrees Celsius, no mass.
Hey!
No mass.
Hey!
Oh, okay.
Stop
Oh,
running!
minus thing.
Yeah, I know. There's 3 kinds, but you're only going to need the specific one.
Okay, okay. Let me take a note real quick.
I have a
Motherfucker.
Yeah, go ahead, hon. Go ahead.
so for a gas phase reaction,
Yes.
gives us the temperature of 2 gases.
Okay. Yes.
The temperature of 2 gas products, can we determine how much the product is being made with the percent yield? Is that what that was?
Yes, yes. This one is pretty much. Let me look at it again. Hold on. Yes, yes. So the question that you're asking about that he mentioned in lecture, this is what it is right here. So you're given a temperature, 2 pressures, a volume, and a percent yield. And yeah, this is how you do it. So you're going to use PV equals nRT twice to find moles, turn it into the moles of the product, and then you can see which one you have a smaller amount of, and that's going to be your theoretical yield.
The smaller is the theoretical, and then we don't have to like add them or anything.
No, then you have your theoretical yield of product, and you multiply it by the percent yield to get the actual yield, and that's what's the 3.87.
Cheater.
And also,
Yeah.
Ever.
Yeah. So you divide your percent yield
holding
by
your breath so
100,
hard.
then multiply it by the theoretical.
Yeah.
Yeah, go ahead, hon.
okay, so for chapter 10, I think
Yes.
it's page 18. So there is some sort of like letter. I basically not sure like which one is which one. Like,
All right.
so
That's
chapter
good,
10, page 18. Molar mass and density and.
Okay. So this one is, let's put these in like better to understand stuff. So PV equals
An RT, like more.
well, so moles is mass divided by molar mass. That's what this is. So this mass divided by molar mass.
Okay.
Because that equals moles, right? Like if you have, yeah, okay. And then
Yeah.
times RT. So this is one useful way to have the equation. And
For the little right hand side, the D equal to MV. What does that M and V refer to? Is that M mass?
mass over volume, yeah. So this is density equals mass over volume.
Do this one.
So the density of a gas is equal to
Pressure.
times molar mass
Oh, okay.
RT. Yeah, and that one,
Oh, okay.
that one is useful. You want that one.
Okay, okay. Cool.
Yeah. In fact, it would be safe to have both of those.
Okay, cool. Sounds very good.
All right. Good luck.
Okay, thank you. I think that's it for me. Okay, thank you very much and have a good night.
You're welcome. You too. Bye.
Bye bye.
Oh, this is Mari.